Welcome to PCTricksGuru.com. This is Ashutosh, and today we will be learning about the conversion between number systems. So, as we already know that we have four kind of number systems: decimal, binary, octal, and hexadecimal. Decimal numbers, they are represented with base 10, and it contains the numbers from 0 to 9. Binary numbers, they are represented with base 2, and binary contains the numbers 0 and 1 only. Octal, it is represented with base 8, and it contains the numbers from 0 to 7. And hexadecimal, it is represented with base 16, and it contains the numbers from 0 to 9, and 10 to 16 are represented as A, B, C, D, E, and F. So the first conversion which we are going to do is decimal to binary. I've taken an example 25 base 10, and we want to convert it in base 2 number. So write 25 here like this 25 and divide 25 by 2. After dividing 25 by 2, we get 12 as the quotient and 1 as the remainder. Now again divide 12 by 2 and you get 6 as quotient and 0 as remainder. Now divide 6 by 2 and we get 3 as quotient and 0 as remainder. And if we divide 3 by 2, we get 1 as the quotient, 1 as the remainder. Now 1, it cannot be divided by 2 further, so we get quotient 0, and 1, it will be taken as the remainder. Now after getting these remainders, we have to write them down from bottom to top. So it goes upwards. So the base 10, 25 base 10, it can be written as 11001. So it's 11001, and we put the base as 2. So 25 base 10 is equals to 11001 base 2. So we have one more example here. So I've taken 34 base 10 and I want to convert it in base 2 number. So we have to follow the same process again. 34 divided by 2 and we get 17 as quotient, 0 as remainder. Now do the same thing, divide 17 by 2, we get 8 as quotient, 1 as remainder. So at the end we get 0 as quotient and 1 would be taken as the final remainder. Okay, so 34 base 10 equals to 1000010. So it's here 34 base 10 equals to 1000010 base 2. So we have one more method, it's the shortcut method. So if I scroll down, you can see it here. I've taken the same example from the previous ones, 25. So it has a different logic. Before starting the conversion, we have to write this series here: 1, 2, 4, 8, and 16. So 1 multiplied by 2 gets 2, again 2 multiplied by 2 gets 4, then 8, then 16. So 25, what we have to do, we need to sum up the numbers which we got here in this series, and the sum, it should start from the higher number and it should go towards the lower number. So to get the result as 25, I've taken 16 here, 16, and then add the next number, we get 16 plus 8. And now if we take 4 or 2, the sum would be greater than 25. So 1, it satisfies this condition here. So we have written 16 plus 8 plus 1. Okay, so 16 plus 8 plus 1, it gives us the result 25. So after writing these numbers, 16 plus 8 plus 1, these numbers would be represented as 1, and the remaining numbers from the series would be represented as 0. So 16, we write it 1, 8, it's already here, so we write it 1, 4 and 2 are not taken, so we have to write 0 and 0 in place of 4 and 2, and 1 it's already taken, so it's 1. So the final result which we get is 11001. So this is the binary equivalent for 25 decimal number, which is written here. In the same way, I have taken one more example, the 32, and not 32, it's 34. So you can have a look at the example. It's easy to understand. Now let's move to the next conversion type. It's a decimal to octal conversion. So the logic is same as the decimal to binary. So instead of 2, we take the number 8 as base here. And while performing the operation, the division operation, we will use 8 instead of 2. So write 137 here, divide it by 8. After dividing 137 by 8, we get 17 as quotient and 1 as remainder. Again, divide 17 by 8, we get 2 as the quotient and 1 as the remainder. Now 2, it cannot be divided by 8 further, so we write 0 as the quotient, and this 2, it's taken as the final remainder for this conversion, for this calculation. Now again, move upwards to 1 1. So the octal equivalent for 137 decimal number is 211 base 8. One more example is here for you. You can have a look at this, and it's easy to understand, so I'm not going to repeat it. Now let's move to the third type of conversion. It's decimal to hexadecimal. So I've taken 223 base 10 and we want to convert it in the base 16 number. So let's start. Same logic applies here as well. Instead of 2 or 8, we will divide the number by 16. So write 223 here and divide it by 16. It gives us 13 as the quotient and 15 gets remainder. Now 13, it cannot be divided by 16 further, so we write 0 at quotient, and 13 would be the final remainder. Now write these numbers upwards, so 13 and 15 and base 16. So the hexadecimal equivalent for the 223 decimal would be 13, 15, base 16. That means we represent 13 as D in hexadecimal number system and 15 is represented as F in hexadecimal number system. So the final result would be DF base 16. All right, so here's one more example. The same thing is being followed here. 16, we need to divide 348 by 16. 21 is the quotient, 12 is the remainder. The same steps again, and the final remainder is 1. Count them, take them upwards, 1, 15, 12. I'm sorry, 1, 5, and 12. So here, 1, 5, and 12. 12 can be represented as C in the hexadecimal system. So the overall result for 348 base 10 would be 15C base 16. Now the next conversion is binary to decimal. This one is also easy, only the method is different. So we have taken binary number 11001 base 2, and to convert it into decimal, we start writing it from right to left. So first we take 1, then we take 0, then we take again 0, 1 and 1. So 1 0 0 1 1. Now after writing 1, we have to multiply it by 2 to the power 0. Remember, the power starts from 0 and then it increases by 1 while we go from right to left. Okay, so 1 multiplied by 2 to the power 0 plus 0 multiplied by 2 to the power 1, then 2 to the power 2, 2 to the power 3, 2 to the power 4. Let's go from right to left and keep increasing the power value by 1. Okay, so if we solve this, we get 16 plus 8 plus 0 plus 0 plus 1, that is equals to 25. So we got 11001 binary base 2 is equals to 25 base 10. Again, one more example is here, 100010. Write it from right to left, 010001 here, and then follow the same thing. 0 multiplied by 2 to the power 0 plus 1 multiplied by 2 to the power 1, then 2 to the power 2, 3, 4. The series follows here, and then solve the whole equation and you get 34. So the decimal equivalent for binary 100010 is equals to 34 base 10. Next one is octal to decimal. I've taken 211 base 8 and we want to convert it into the base 10. So the thing is same, write it from right to left, 1, 1, 2, 1 plus 1 plus 2, then 8. Write the base number here and add the power 0, then 8 to the power 1, 8 to the power 2. So this conversion follows this series. After solving this equation, we got 137. So 211 base 8 gets 137 base 10. One more example is here. You may have a look at this. And the result of 70 base 8 gets 56 base 10. Okay, so the next conversion is hexadecimal to decimal. So I've taken an example, DF. D can be written as 13 and F can be written as 15. So write 15 into 16 to the power 0 plus 13 into 16 raised to the power 1. If we solve it, we get 223. So DF base 16 is equivalent to the 223 base 10. Again, one more example is here, 1, 5, C. C can be represented as 12. So we write 12 plus 5 plus 1 and follow the same rule, 12 into 16 to the power 0 plus 5 into 16 to the power 1 plus 1 into 16 to the power 2. And if we solve it, we get 348. So for the decimal equivalent for 15C hexadecimal is equals to 348 base 10. Now converting the fraction part, and you can see the example here. So first of all, we need to convert 62 into the binary. The method is same, so you can just keep dividing it by 2 until you get the final quotient 0 and remainder 1. So if we convert 62 into binary, we get 111110. Now for the fraction part, we have to write 625 and then multiply it by 2. So it's 0.625 multiplied by 2. It gives us the result 1.250. Now again, take this part which is after the point and right here 0.250 and again multiply it by 2, which gives us the result 0.500. Now take 0.500 here, multiply it by 2 and it gives us the result 1.000. So we got 1 here and we can end the multiplication here because we got 0 at the right side of the decimal point. So if we write it here, it goes 62.625 base 10 is equals to 11110, this part, 0.101. And what we are doing, we take this part from bottom to top, and while writing this part we have to go from top to bottom. So I've taken 101. It looks same because whether we go from top to bottom or bottom to top, it looks same, but the rule is that we have to go from top to bottom, so it's 101. Okay, so this is the result. Now let's move to the next example. Next conversion, it's a decimal to octal. So The same concept is being followed here. 29 has to be converted into octal using the previous method which we learned. So 29 is equals to 3, 5. Here we have written 3, 5, and 30 we have to write 0.30 and multiply it by 8 because we want to convert it in the base 8, so we have to multiply it by 8. So 0.30 by multiplied by 8 equals to 2.40. Now take this 0.40 here and multiply it by 8 again. It gives us the result 3.20. Now again take this 0.20 here multiplied by 8. It gives us the result 1.60. Then 0.60 by multiplied by 8 gives us 4.80, and 0.80 multiplied by 8 gives us the result 6.40. Now here you can see that 0.40, it's already available here, 0.40. So that's why we have to stop here, because if we write this 0.40 here, it will keep repeating itself and there's no need to do that. So when we got the repeating number here, we have to put an end here, and then from top to bottom we have to write this part which is before the point. So it goes 2, 3, 1, 4, 6. So this part would be 3, 5 point 23146. So here 29.30 base 10 can be written as 35.23146 base 8. So this was the decimal to octal conversion. Now we have conversion of other base fractions to decimal. So here's one more conversion. Let's go. It's octal fraction to decimal fraction. So I've taken an example. 45.352 base 8 equals to base 10. What would be the value here? So write it in this way. 45.45, convert it into decimal as we did earlier. 8 multiply it by 8 to the power 0, then 8 to the power 1. So the left side part would be written as this, and for the right side we have to go from left to right. Here we are going from right to left, and now for the right side we have to go from left to right. So write 3 plus 5 plus 2 and then multiply it with the base number and raised to the power minus 1. So here we do not start from 0, we start from 1. So it looks like this: 3 into 8 raised to the power minus 1 plus 5 into 8 to the power minus 2 plus 2 multiplied by 8 to the power minus 3. If we solve this, at the left hand side we get 37, and to the right hand side we get 457. So this value, it can be written as 37.457 base 10. So 45.352 base 8 is equivalent to 37.457 base 10. Now let's switch to the next one. We have a binary fraction to decimal fraction conversion. So here 10010.101 base 2 is equals to base 10, and we have to find out the value of this question mark. What will be the value here? So write the left part and right part separately. So 10010, actually it would be written as 01001, 0 plus 1 plus 0 plus 0 plus 1. Now multiply it with 2 raised to the power 0. Start from the right side here. So I have written 2 raised to the power 0, then 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, and 2 raised to the power 4. So we are done with the left side part. Now for the right side part, we have to follow the rule which we followed in the previous example. We have to go from left to right. We have to start the power from 1 instead of 0, and we have to keep a minus sign there. So I start with 101 here, 1 plus 0 plus 1, and then 2 to the power minus 1, 2 to the power minus 2 and multiplied by 2 to the power 2 to the power minus 3. And if we solve this whole equation, we get 18.625. So this is the decimal equivalent for this binary value. Okay, now the next part is interconversion. So we have two kind of interconversions available. It's a binary to octal and a binary to hexadecimal. And to create binary to octal, we need to create a group of 3 digits, and for binary to hexadecimal, we have to create a group of 4 digits. How it is done, let's see. So the question, the value which we have here is 100,000,111,010,110,1111 base 2 equals to base 8, and we have to find out the value of this question mark. So as we already know that we have to go from right to left, write these numbers from right to left, but the condition is that we have to write these numbers in a group of 3. So we take 111 as the first group. Now we take 101 as the second group. Now we take 110 as the third group. Now we take 001 as the fourth group. Now we take 000 as the fifth group, and 1. Now we cannot form a group of 3 because we have 1 left. So to do this, to create a group, we need to add extra zeros to the left of 1. So 1 is written here and then 2 extra zeros, so it becomes 001. Okay, now write the decimal equivalents for each group. So for 111 we have the decimal equivalent 7, and for 101 we have 5, for 110 we have decimal 6, 001's decimal equivalent will be 1, for 000 it would be 0, and for 001 it would be 1. So if we write this value base 2, then the octal equivalent for this binary value would be 101657. So it's 101657 base 8. Okay, and if the binary number contains fractions, you can follow the same grouping rule for the fraction part, but the zeros will be added to the right side of the fraction part. See the following example. So what is being shown here, that this part is okay, you already know how to convert this part, but for the part that is on the right side of the point, we have to follow a little different method. Instead of going from right to left, we have to go to left to right during the conversion, and instead of adding the zeros before the number, we have to add the extra zeros after the number. Like see, 100, the first group of 3 digits has been 100, then 11. So after 11 we have to add one extra 0 and extra 0, so it becomes 110. Now write the decimal equivalents for all of these groups and you'll get the final result as 101657.46 base 8. Now we have a binary to hexadecimal. So we have the example 10000011101111 base 2, and we have to convert it into base 16 equivalent. So write the numbers in the group of 4 starting from right to left. So I have taken the first group 1111, then the second group would be 0101. It's here. Then the third group would be 1100, and the last group would be 0001. So after converting these groups into decimal equivalents, we get 15, 10, 3, and 8. So 8 and 3 are fine, but in hexadecimal number system, 10 is represented as A and 15 is represented as F. So the final value, the final hexadecimal equivalent value for this binary value would be 83AF. And if the binary value contains the fraction part, then we have to do this thing. Convert the left-hand side part as usual as we converted in the previous example, and for the right side part, create a group of 4 by adding an extra 0 to the right side of the number. So it becomes the 101, it becomes 1010. Now write down the decimal equivalent for all these values. So 1000 becomes 8, 0011 becomes 3, 1010 becomes 10, 1111 becomes 15, and 1010 becomes A. So this will be the final outcome, 83AF.A hexadecimal base 16. So I hope the things are clear now. You might have understood the conversion between number systems. So that's all for today. I will be thinking to create another video very soon. Till then, have a good day. Bye bye.